Okay. Hello, everyone. We're going to go ahead and get started. We are at 4:17 p.m. on Tuesday, January 14th, and we are here on the second day of press conferences at AAS 245 in National Harbor. We are here this afternoon for the session New Information from Milky Way Highlights. For those of you watching online, we have switched our internet connection from the wired to the wireless. We hope that this will make things better instead of worse. Please let us know if we drop out at any point. I'm not sure we can do anything about it, but we'll try. So my name is Susanna Kohler. I am the press officer for the AAS, and I am joined here today by Carrie Hensley, the deputy press officer. Amy Oliver from SAO will be running the mic during the Q&A session. And we've also got Lexi Galt, our AAS Media Fellow and a graduate student at Indiana University, who is assisting us online. And let's see. We are excited for the session ahead. Before we get started, just a note to silence any cell phones or anything else that might make noise. And also note that we are, in fact, recording this and streaming this to YouTube live. The video is going to be archived there later, and we'll have links to the videos from the briefings as well as any materials such as press releases and the slide decks from the presenters. We'll have that updated by the end of the day. And I believe I actually didn't ask, do we have press releases coming from all of you? Yes, I'm seeing yeses. So we're going to have 4 press releases coming out from this session as well. So with that said, for anyone who hasn't attended a AAS press conference before, the way we're going to do this is I will give a brief introduction here and I'll introduce our speakers. And then each of them is going to present back to back in turn. And we ask that you hold your questions through that time until we get to the second half of this, which will be a Q&A session. So at that point, we'll go to Q&A for all of the speakers at once. We've got a handheld mic, which will run around the room. And so you can ask your questions at that point. We ask if the mic comes to you that you identify yourself and your affiliation and who your question is for. For those of you who are watching online on Zoom, you can ask your question at any time using the Q&A feature there. You can type it into the box. Please, when you do so, also type your name and affiliation and who your question is for. And we will read those aloud during the Q&A session at the end. So that said, let's get underway. As I said, this session is titled New Information from Milky Way Highlights, and this is our chance to revisit a lot of old favorites in our galaxy with maybe some pretty new images. And in fact, there are a lot of pretty pictures here. So if that's what you're here for, you're in the right place. First up, we're going to have Jacob Jensen from Caltech and IPAC, who's going to present on infrared echoes of Cassiopeia A and how they reveal the dynamic interstellar medium. Then Josh Peak from Space Telescope Science Institute will present a path-breaking observation of the cold neutral medium of the Milky Way through thermal light echoes. Then Joel Kastner from RIT Center for Imaging Science will present imaging an astronomical icon in 3D, a new view of the Ring Nebula. And last up, Danya Alboslani from the University of Connecticut will present on X-ray echoes from Sag star and how they provide insight on the 3D structure of molecular clouds in the Galactic Center. And Samantha Brunker from the University of Connecticut is also here to help in the Q&A session. So with that, I'm going to go ahead and get this set up and turn it over to Jacob.
Hi, everyone. Thanks for waiting a bit. My name's Jacob Jensen. I'm from Caltech and IPAC in Pasadena, and I'm really excited to be here today to tell you about a new observing program we're conducting with JWST that is giving us a really spectacular view into the detailed structure of what we call the interstellar medium. And so I'm going to give you the whole story of how we got here and why I think you should find this as exciting as I do. But I want to show you what we're going to be looking at first here. And so what you're seeing here, mostly in red, are the detailed structure of an interstellar cloud of material. So this is all the material between the stars being illuminated by the flash of a centuries-old supernova. And so what you're seeing as these apparent filaments appear to move is not real motion of the gas, but just the propagation of this light propagating through this cloud and illuminating different parts of the cloud as it moves through. And so why I think you should find this important is because this cloud is made of all the material that exists between the stars in our galaxy and is also the material that can collapse to form new stars and planets like the one we live on. And so this detailed structure like this has never been seen before. And it's only because of the properties of the echoes of Cassiopeia A that are giving us this really detailed view that we can now see with JWST. And so Cas A, of course, is a famous supernova remnant. It's among the youngest supernova remnants in the galaxy and also among the closest of the core collapse type. So this was the explosion of a massive star that happened centuries ago, and the light from this explosion first reached Earth about 350 years ago. And this remnant is the brightest object you see in this image. And it's, of course, been studied by many telescopes, including recently by JWST. And so there are beautiful images of the remnant itself, which happen to have one of these echoes that lies just behind the remnant in the corner down there that is labeled the baby Cas A. But there are actually an entire system of echoes surrounding this object in the medium of gas and dust around Cas A that are illuminated by the light from the supernova and glowing in infrared. These were first discovered by Spitzer almost 2 decades ago now, and have been continued to be monitored by the NEO-Y satellite until the end of its mission earlier last year. And so these echoes are actually from the light, the first light from the supernova as the explosion blasted through the outer layers of the star. It released a burst of UV radiation that lasted only a few days, but continued to propagate out into this material and continue to interact with it, to this day so that we can observe. So this flash is heating up dust and gas in the interstellar medium and causing it to glow in the infrared, what we call an infrared echo. And this is why we can still observe them today. And one thing that is really amazing about echoes is just like an echo in this room, if I yelled really loud or clapped, the longer it takes for me to hear that echo come back to me tells me how big this room is, because the sound had to travel there and then back to me. And we can play the same game and do the same thing with light echoes. The longer it takes for the light that is interacting with this material to come to us tells us how far away it is from the original source and actually gives us its 3D location in space. And so this now in this diagram I'm showing you is like a side view, a slice through the image, and it's showing us where these echoes lie because we know the time delay since the first light from Cas A came to us. We can determine exactly where they lie in these regions behind Cas A. So the echo labeled W1 in red is the one we're going to focus on. And the other thing I want to emphasize or show you is so cool about these echoes is that by taking a time series of imaging, you can actually reconstruct the full 3D geometry in real 3D space of what the structure of this gas and dust is. And also because the pulse was so short, only a few days long, it gives us an extremely thin slice through this material at each step. So I'll start this movie. Hopefully you can see it. So we're seeing the images. The orange emission is the monitoring by NEO-Ys as the echoes have continued to propagate over the years. And we can turn that into a real 3D geometry of this dust cloud where we're seeing slice by slice the echo propagate through the cloud. And so analysis of the Spitzer data indicated that this material was highly clumped, possibly filamentary structures, and gave us scales of something like half a light year. So this is less than the scales of, say, the distance from Earth and the sun to the nearest star system, which is a few light years away. And so we're already able to see structures sort of on the scales of star systems. But of course, with the resolution of JWST, we can peer deep into these clouds and get this almost medical CT scan through the cloud with the exquisite resolution of JWST, a 50-fold improvement over previous observations with Spitzer and NEO-Ys, and actually scales comparable to individual stellar systems themselves. And so access to these scales is giving us, opening a window to whole new regimes of studying fundamental physics of how these structures in the interstellar medium form and how structures like this could potentially collapse into new stars and planetary systems. And you're going to hear a lot about this also in the next talk by Josh Peak. So I want to call that out as well, my collaborator. And so this is, again, what the echoes looked like in 2024. NEOWISE happened to catch them one last time before the science mission ended in July. And this is what we see when we look at it with JWST. And there's something else I really want to highlight. I think this image, while extremely beautiful, also gives us something immediately that we can see about how these echoes are so powerful in determining the structure of the interstellar medium. So you'll notice at the bottom on the left side of this figure, there's this fuzzy, hazy material that is kind of glowing in a bluish or maybe brownish color. And this, we think, is essentially the same material that is being illuminated by echoes, but it doesn't look as detailed at all. You may have noticed the same structure actually showed up in the background Spitzer images that I was showing on previous slides. So this is the cold dust and gas of the ISM, but without these thin slices through the cloud that we get from the echo, even with the resolution of JWST, you can't make out this beautiful 3D structure of these clouds until the echo propagates through. And so, you'll also maybe notice, and you'll hear about this more in the next talk, that there are different kinds of structures, knots, bundles. And so this is going to be a really fantastic, rich data set to figure out, how all these structures fit together and determining this real 3D structure of these interstellar clouds for essentially the first time. So I want to give you a little peek to other things we're going to do with this data set. We're getting spectroscopic data as well. And so we're in the process of getting a sequence of what are called spectral image cubes. So we use the MIRI instrument. And what I'm showing you in the images here are the field of view that we observe with MIRI, and then what it looks like in this image cube. And what you get, why we call it a cube, is that because for every pixel in this data cube, we get a spectrum of what this dust and gas look like as a function of wavelength. So we can see features of all the molecules and the dust grains and determine the compositions of the clouds. It also gives us important information to constrain the actual light from the supernova that is powering this echo, so we can determine how bright it was. And this will give us important information about the star that actually exploded, because it tells us about the physics of how that explosion burst through the surface of the star 350 years later. And we'll also be able to see, as this echo propagates past the region we're observing, whether there are any changes to the interstellar material that are induced by this energetic UV radiation from the supernova. And so we can see if any, say, small dust grains are destroyed and learn more about how supernovae interact with the material around them and, help determine the properties of the galaxy and the interstellar medium as a whole. So I'll leave up these beautiful images showing both the JWST view of the remnant itself of Cassiopeia and also now the echoes of the interstellar medium of this centuries-old supernova. And just leave you with a few points. One, that this time series imaging is revealing intricate 3D structures down to the scales of individual star systems that are only visible with the combination of JWST's resolution and having Cassai's echoes illuminate this material. We see newly discovered morphologies that look different from the structures at larger scales, which are opening up a new regime in understanding the formation of structure in these interstellar clouds. And we'll also be obtaining spectroscopy in a spatially resolved way that we can determine the composition of the cloud and also look for any signs of processing of these dust grains by this radiation from the supernova. So thank you very much.
Hi, I'm Josh Peak. I'm working with Jacob Jensen on this project. This is an intradisciplinary project. If you think about astronomers, the people who study things that explode in a fraction of a second, and those of us who just study the diffuse interstellar medium are kind of on opposite sides. So we've come together on this project. And I'm going to be telling you more about the interstellar medium implications of this work. So I call this a path-breaking observation because I think this is going to completely change the way we think about the foundations of this particular kind of interstellar medium called the cold neutral medium. I'm listing all of our collaborators here. It takes a lot of different people with understanding of lots of different kinds of physics, lots of different kinds of observing. And it's been wonderful working with everybody, many of whom are in the room here. I talk really fast. There's notes at the top. Sorry. So just the overall zoomed out thing here that has been really surprising to me about this work. I've been working in the interstellar medium for a long time, and if you look at all of these beautiful images from Hubble, James Webb, and many, many, many others, they're always very beautiful, right? But that process of getting from beauty to truth is what all of us astronomers have been working on for, I guess, thousands of years at this point. And it's a very hard process. And this has been a shockingly quick path to go from something that you just see that comes right off the telescope to something that is incredibly impactful in the sense of physics. I was saying we see all these beautiful things. I'm showing the ring nebula here, which my colleagues are going to be talking about in a minute. Complete coincidence. But this is just to point out that usually when you see the interstellar medium, in many of these contexts, you're seeing it lit up by stars. You're seeing a stellar interstellar interaction. And that's incredibly important for stars forming, for stars exploding, for lots of other things, for the processing of the interstellar medium, but it's quite rare. It's actually a very small fraction of the interstellar medium that looks like this, okay? And those are the pictures we always see. And that's what's so magical about this work, is that what we're seeing here is quite common. So this particular piece of interstellar medium, I'm showing the same diagram as before. So you've got Cas A in the center, and you've got our light echo in the lower right, is about 70 parsecs away. The scale upon which star formation happens is the tens of parsec scale, 10 parsecs, few parsec scale. That's where giant molecular clouds work. That's how stars are formed. That's where this supernova went off. But because this light has just reached this thing for the first time, this gas doesn't know about that process. It's too far away. So this we can think of as just a prototypical piece of the interstellar medium floating around. It's about 100 parsecs off the plane of the galaxy. It's about 70 parsecs away. It's in a pretty boring part of the galaxy. Here I'm using another galaxy as a stand-in for ours, since we don't have a terribly good picture of our galaxy from the outside, but there's the sun in yellow and Cas A, and you can see it's just in some kind of reasonable part of the galaxy. So we're not talking about an extreme environment. What makes this work so magical is that this is typical interstellar medium. So one thing we can do by looking at these many images that we have, these are two images separated by 14 days, and you can see the interval. And so you can see this movement effect. But this movement is actually a pulse that's moving through a three-dimensional structure. And if you zoom in into this one little spot, you can see that this plane, this surface, okay, is being illuminated 2 different times. If this pulse were 2 weeks long in time, these should be connected, okay? Because you'd see the pulse, the first pulse and the second pulse, that would be the 14-day increment. Since they're not connected, we know they're shorter, and we're pretty sure that this is a less than a 10-day pulse. It's probably even shorter than that. And that gives us a constraint on the density. We know how bright this thing is. We know how much total stuff is inside the pulse. And so by understanding the time of the pulse, we can get a sense of the density. And so the density is somewhere between about 100 and 500 per cubic centimeter, which squarely makes it cold neutral medium. I want to give you context for cold neutral medium. This is a breakdown of the mass of the interstellar medium. You've got very hot stuff at 1%, and then warmer stuff. And then the CNM is sort of the biggest chunk, or a very big chunk. And this diagram just shows you how important this stuff is. This is a big chunk of the stuff that's out there, perhaps the plurality. But this is also a process. We know that material goes from the warmer phases into denser phases, and over time collapses into stars. But that pathway for forming stars, we don't completely understand. And one of the reasons we don't understand it is we don't understand how things compress when they're magnetized. These structures, the cold neutral medium is well known to be magnetized, and that its structure is oriented with the magnetic field. So when you see this kind of, when we know this must compress, it has to somehow get rid of the magnetic field. And we have fundamentally for many decades not really understood that process. I'll jump back to that, but I want to show you these videos. These are 3 time steps, one that's 14 days apart, and another that's 28 days apart. And I want you to see these 2 kinds of structures that I see. I see knots that look like kind of gnarled woody pieces, and then I see these very long linear pieces, which we call bundles. And if you look with your eye, you'll see another feature, which is that they tend to move differently. When you look with your eye between a knot region and a bundle region, they are moving differently. Now, as I said before, this isn't about the motion of the gas. This is about something stepping through. So if you have one structure, say, pointed this way and another pointed this way, when you step through, they'll seem to move in different directions on the surface of the sky. And that's what we're seeing here. The knots and the bundles are moving separately, meaning that they're somehow structures that are all composed together. And what we think may be going on is that we have crumpled ribbons. Here I have a ribbon, a paper ribbon here. And if you crumple them all together, like I'm doing here with my hands, and you slice it this way, what you'll see is something that looks like the knot. And if you look at the knots, they're pretty static. I'll draw your eye to, can I do this with my cursor? Maybe not. I'll draw your eye to the knot at the very center of the top, and you'll see that thing is very static and very consistent. It's moving slowly, and it has lots of very consistent structure. But if you look at above it, in that really long set of bundles, you'll see they're moving really fast. That's what happens when you take a crumpled ribbon like this and you slice it this way. You see these linear long features, but they move very quickly. So it may be that we have a unified perspective on how these structures work. We're still working on this, but it's really exciting for the first time to be able to get at the three-dimensional structure of the interstellar medium on these incredibly tiny scales. And these scales are incredibly important because that is where we can study turbulence and where we can study magnetism. If we want to understand how stars form, we need to somehow figure out how this gas sheds its magnetic field, which resists the compression. These are simulations by one of our collaborators who is a part of this work, Drummond Fielding. These are incredibly high resolution simulations, the highest ever done of this kind, that are resistive simulations of the neutral medium and, the cold and neutral medium, a so-called two-phase medium. And so what you see is lots of similar qualitatively structures. And the point I'm really trying to get across here is that by studying what we can see in these light echoes, we're going to be able to get at the magnetism, the magnetic structure that is guiding these structures and figure out how these things compress over time to later form stars. So the 4 takeaway points. I think this project exemplifies a rarity in astrophysics, a really short path from beauty to truth. I've been studying the ISM for a very long time, and mostly it's confusing. The second point is that as opposed to most of what we see, these are really common. This is 40% of the mass of the material that we see in the interstellar medium. This is the pathway towards star formation. So studying this, when I showed this to one of my collaborators, Eddie Schlafly, he said, "You're telling me that every cloud in the sky is an onion?" And I was like, I guess that's what I'm saying. So it's pretty wild. We see the structure being composed of these bundles and knots, which indicate this possibly crumpled ribbon morphology. We're still studying that, but we do see these things moving independently, so we see these independent structures. And simulations see these similar structures. And these magnetic fields are really important to understand because they resist this compression, which is how all of us came to be. So I will leave it there. Thank you.
Maybe we'll start from the right place this time.
Hi, I'm Joel Kastner from Rochester Institute of Technology. We have Joshua, Jacob, and Joel up here. So very thrilled to be able to give you a brand new view of an old astronomical friend, the Ring Nebula. And I've listed my collaborators here, too many to mention, but I will, without pointing fingers, say Diana Ryder and Paula Moraga-Benz, 2 students from RIT who have worked closely with me and are presenting here as well, are present in the room. And the work I'm going to show you was funded by an NSF grant. Thank you, NSF. So first of all, let me give you about 30 seconds of background on what planetary nebula is. Planetary nebulae allow us to cavort across the entire Hertzsprung-Russell diagram, which I'm showing you here. They begin as main sequence stars between about 0.8 and 8 solar masses, we believe. When those stars run out of nuclear fuel and have generated lots of carbon and nitrogen and other good stuff that we need for life on Earth and on exoplanets and so on, they puff themselves up into red giant stars, and they develop very cool exterior atmospheres that are rich in molecules and dust. They're so cold. And actually, the star becomes about 10,000 times as luminous as the sun. That's an awful lot of pressure power in the form of radiation that can push, along with pulsations, can actually push the material away. So the red giant's envelope is ejected, and that exposes the core where the nuclear fusion has been going on. And that core is extremely hot, starts out at tens of, if not hundreds of millions of degrees. And by the time we see it, it's cooled down to a mere couple 100,000 degrees. Planetary nebulae have some of the hottest stars known at their cores. And that ultraviolet from the core of the star generates the planetary nebula that we know and love in many images from ground-based photography and also from Hubble Space Telescope. And the ultimate fate of these, the cores then is to become a white dwarf, which is just going to cool forever in the interstellar medium. And the Ring Nebula perhaps needs no introduction. Many of us were introduced to astronomy perhaps by looking at the Ring Nebula through a telescope and saying, I see a bunch of stars and then I see this whole smoke ring. What the heck is going on with that guy? So the Ring Nebula is iconic, but the intrinsic structure of the ring has been debated for over a century now. You can go back to papers by Kohler from 1899, all the way up to the latest James Webb Space Telescope images, which you just saw flashed in front of you. And every single one of those papers, with some exceptions, is concerned with what is the actual structure of this thing anyway? Is it a smoke ring? Is it a ring like you put on your finger? Is it somewhere in between? And in addition, the Ring Nebula is the archetype, if you like, of a molecule-rich planetary nebula. So despite the fact that you've got a very hot central star that's exposing the gas to lots of ultraviolet radiation, a lot of molecules remain intact in these objects. But the only previous millimeter wave imaging of carbon monoxide and other molecules in the Ring Nebula, it now dates back about 30 years ago. Well, carbon monoxide mapping, I should say, dates back about 30 years ago. No one else had looked at the Ring Nebula until we used the submillimeter array this past year to look at carbon monoxide in the Ring Nebula. The motivation was to understand the distribution and the motions of the molecular gas in the nebula, so we could try to understand the origin of the molecular gas and perhaps more about the structure of the Ring Nebula, trace the mass loss history of the red giant progenitor star that generated the Ring Nebula, perhaps look for evidence of interacting binary companions. I didn't mention it when I showed you that Hertzsprung-Russell diagram, but we have a feeling that presence of a binary companion will fiddle badly with that simple scenario I showed you and change things dramatically. So we obtained our submillimeter array maps at a wavelength of 1.3 millimeters in the spring and summer of 2024. We looked at emission lines of carbon monoxide. We had a field of view. It's about a tenth of a full moon in each direction, 180 arc seconds by 180 arc seconds. And the unique thing about these observations is the combination of really good spatial and velocity resolution. So I've got a movie here, and you can see the QR code. Thank you, Amy, for putting this here. You can snap that if you like. It's going to be available. I think it isn't already available from the RIT Center for Imaging Science YouTube channel. And I'm just going to quickly try to narrate my way through this. There are subtitles, thankfully, because I might get lost otherwise. There's a lot going on in this roughly 5-minute movie. The Ring Nebula, as I've just mentioned, is among the most photographed celestial objects. Recently was a subject of JWST infrared imaging. Here's an image of molecular hydrogen with JWST and at a wavelength of 2 microns. This is an image of small dust grains, carbon dust grains, and you can see the central star at a wavelength of 3.3 microns. Now we've obtained radio wavelength images, wavelength of about 1.3 millimeters with the sub-millimeter array. That's the carbon monoxide view, but as I said, we have velocity, really good velocity resolution here. So we can take these data and produce a data cube, which you just heard about in the previous talks. Different way of looking at 3D data, because we've mapped the millimeter wave radio emission. We can very accurately measure blue shifts and red shifts in the CO emission, and that's what gives us this additional dimension. So we can not only see the position, x, y, but we can also see the velocity dimension. And we can translate that velocity dimension into a physical dimension because we know that the Ring Nebula is expanding in three dimensions. Now we know that the gas resides in this sort of clumpy shell. We can see it right here in the submillimeter array data. So we can build a very simple 3-dimensional geometrical model of the ring's 3D structure. And we best model this as a triaxial ellipsoid that's truncated at each end. That's a fancy way of saying this is a barrel-shaped object, but it's not cylindrically symmetric in the least. It's ellipsoidally symmetric, if you like. And we can now determine that the gas was ejected, the molecular gas was ejected from the star about 6,000 years ago, because we can construct this model. But then we look at it and we say, oh, it's got these holes, and those holes appear to be caused by a faster outflow along the polar axis, but not quite along the polar axis. It's tipped by about 10 degrees. And that younger outflow seems to be, as I say here, slightly tilted. And that suggests that there is probably a binary companion that's responsible both for driving these fast outflows and after the red giant ejected its outer layers and formed the main ring. So it's the interactions with the companion star that likely generated those high velocity polar flows. I'm still spinning this for you just because I just love to look at it in 3 dimensions. It blows my mind. This is again the 2-dimensional view if you collapse the data cube down in velocity space. And now we can learn more by looking at the comparison of the submillimeter array and JWST images about the ring structure. First of all, we can see that if we look at the velocities that are moving perpendicular to us, that's showing us how the molecular gas perfectly outlines the ionized gas. It's a very thin shell of molecular gas. There is no molecular gas essentially embedded inside the nebula. It's all sitting around outside. That tells us that it's a fossil remnant of the red giant star. We can also now very carefully examine the position of the central star because we've got the JWST images, we've got the SMA images. We can look at where the central star lines up inside the nebula quite precisely. And now we know, yes, the central star is at the center of the nebula. That was not a foregone conclusion if you look at the JWST images and previous images, because it's off center in that with respect to the central hole. That's just a result of our viewing angle and the fact that it's got these tipped cones, if you like, that are tipped holes that are not quite lined up. And we can see the high velocity gas and dust too. That's a remnant, we think, of this fast outflow that's younger and has exploded through the previously ejected ellipsoidal shell. I think that's the full story here, but I got to run the credits because this is a movie. I made it with iMovie, and you got to use all the bells and whistles here. So again, this is the 3-dimensional view, just to show you one more time. It's really fun for us to be able to image this astronomical icon, if you like, in 3D. Again, here are the collaborators. This paper has just been submitted to the AppJ at about 11:30 p.m. last night. That's why I may be kind of a little bleary-eyed right now. And again, thank you, NSF, for helping to support this work. Thanks.
Hi, everybody. Thank you for coming. My name is Danya Alboslani, and I'm a postbac at the University of Connecticut, who's also applying to grad schools. So if you see my application on your desk, I hope you watch this and consider me for your program. What I'm really here to do is to tell you about the 3D models that we have made of the molecular clouds or star-forming clouds in one of the most extreme environments in our galaxy. We also are able to constrain the past flaring events of Sagittarius A star, our supermassive black hole in the center of the galaxy. So in the past, Sag A star has accreted material and emitted X-ray flares that propagate in all directions. These X-ray flares interact with the molecular clouds through a process called fluorescence, which I will explain in depth at a later stage. So as the X-ray light travels through the molecular clouds, they will highlight slices of the molecular clouds over time, like an X-ray scan. And we have observed 2 decades of these X-ray echoes from the Chandra Observatory and compared them to the submillimeter array data and actually created 3D models of clouds. If you are further interested after this presentation, we have 2 manuscripts available on arXiv later today. So first, I just want to give some background on our Galactic Center. So this image here is an image of the inner 300 parsecs of our galactic center called the Central Molecular Zone, or CMZ. And it is an extreme environment where the gas densities, turbulence, and temperatures are over 10 times higher than in the rest of the Milky Way. The CMZ is a way station between gas inflowing from the galactic disk and gas interacting with the black hole Sagittarius star. Astronomers use this region to test star and planet formation theories, gas dynamics in extreme environments, and black hole physics. However, there are still many mysteries that remain. For example, it is super difficult to create 3D maps of molecular clouds and their orbital motions, which is essential for understanding both star formation and gas flows in the Milky Way. So in this project, we're actually modeling two clouds, the Styx and the Stone cloud that can be seen here, through X-ray echoes. In addition, the supermassive black hole Sagittarius A star holds many mysteries of its own. For example, we know that Sagittarius A star is mostly dormant with occasional outbursts, but we do not know the durations of these outbursts, how often they happen, and what types of impact they have on the surrounding environment. So I'm just going to explain this process again. So in the past, Sagittarius A star has accretion events that has caused it to propagate X-rays in all directions. We have not observed the light directly from Sagittarius A star because this happened long ago in the past, and we didn't have X-ray observatories at the time to detect the X-rays. However, as the light propagated out, some of that light interacted with molecular clouds where they have absorbed that light and then re-emitted that light back to us. And we know that as fluorescence. And so the X-ray light that is reflected back to us, we usually call X-ray echoes. And so over time, as the X-ray echoes propagate through, or as the X-ray light propagates through the molecular cloud, they highlight different cross-sectional slices of the cloud, essentially scanning the cloud. And so we can use the time lag between each observation as a third axis in modeling these clouds. And so here are the Styx cloud on the left side and the Stone cloud on the right. And for this particular study, we have observed X-ray echoes or X-ray data from 1999 to 2017. And we see X-ray echoes begin from the Styx cloud in 2010, and then in the Stone cloud in 2008. So something else that we do is compare these X-ray echoes to molecular gas data that has been collected from the submillimeter array. And so in this image, we have the Styx cloud, and in the grayscale, we have the molecular gas. And then the X-ray contours are the X-ray echoes that we have detected from the Styx cloud. And so the X-ray echoes follow the molecular gas really well. And so we can say that it accurately highlights the densest parts of this molecular cloud. And so we do the same thing for the Stone cloud as well. And in this image, the X-ray echoes are actually in the white contours, and then the molecular gas is just, the structures are colored in the background. We do see that most of these molecular structures are corresponding to the years of data. However, there are about 3 structures that we do not see in the X-ray echoes. And so this is kind of not surprising because X-ray data is not continuous. And so we can actually hide some of these structures in the missing gaps. And so we compute the separation between the X-ray observations and also the diameter of the structure in molecular gas. And we were able to place constraints on the duration of the X-ray flare. And so the way that this works is that if the duration is actually longer, then each one of these years that you can see as colored on the plot would actually have a larger width. So if the widths are too long, they can either become overlapping, or they just are like, the separation is so small that it's impossible to hide the molecular structures. And so our study shows that the duration of the X-ray flare can be no longer than 5 months. And so just as a summary, we introduce a new method that highlights dense molecular gas over time, and we can use the time lags from each X-ray observation to create a 3D model of molecular gas or of molecular clouds. We match what we see in X-rays to molecular data, and then we use what we don't see to place constraints on the duration of this event. This novel method lends insight to the 3D structure of molecular clouds in extreme environments, the overall geometry of the central molecular zone, and the past flaring activity of Sagittarius star. Thank you for listening.
Excellent. Thank you so much. We are now going to go ahead and move into Q&A. So if I could borrow Amy for her mic running expertise. Thank you. So if you have questions in the room, just raise your hand and we'll bring the mic around to you. And remember to please identify yourself and your affiliation and who your question is for.
Hey everyone, I am Ziwei from Purdue University. I'm first year graduate student, so I am doing the 3D reconstruction of the Crab Nebula. So I want to ask a question about Jeff. So when I do the 3D reconstruction of the Crab Nebula, the first problem to me is I need to find the center of the expansion, and I also need to find the origin of the 3D structure. So I want to ask you how you do that for the Ring Nebula, how you find the zero velocity, and also how you define the origin of your data.
Those are great questions. So the zero velocity we can get by integrating all of the carbon monoxide emission and producing a spectrum, and then looking at the symmetry in that spectrum. And from that, it's pretty clear what the systemic velocity is. And for those of you not used to dealing with redshifts and blue shifts, from an astronomical object, you can see the expansion in the redshift and blue shift. You can also see the entire object moving towards you or away from you. And so we can gauge that motion of systemic velocity, I would say, to within a kilometer a second or so. So that's how we can get the velocity center. And then we use the spatial correspondence between the SMA's ability to point in the sky and JWST's ability to point in the sky to see where the central star is. In your case, I guess you've got a neutron star in there that you can probably pinpoint. So it's the same general problem. Yeah. Sure.
Hi, this is Charles Day from Physics Magazine, and this is a question for Danya. So you could constrain the duration of the X-ray flare. Can you also constrain its profile, how it goes up and down in time? Sorry.
So yes, you can constrain the profile, like the you can constrain the profile, but previous studies have already done this, and so we already know what that light profile looks like for certain clouds. So for some clouds, the light over time just kind of goes up to a peak and then comes back down. But if the duration is longer, then that light profile won't just do like a peak and then go down. It will kind of have like a little bit of a zigzaggy look to it. But there have been many studies that do this previously, but I have not done this, at least for this project.
Thank you. Rick Feinberg from the AAS and Sky and Telescope. Follow-up question for Danya related to what Charles asked, which is, can you determine from these light echoes the flare frequency and whether there's any hint of periodicity?
So that's a really good question, and the answer to that is I'm not really sure. I would definitely have to look more into that, but that's a really good question.
We've got some questions online.
This question is for Jacob from Bill Waller at the Galactic Inquirer. Can you clarify what you meant by the scales of individual stellar systems?
Sure, yes, I can do that. So the scales I was talking about are about 500 astronomical units. So this is, the scale of resolution we can see in 3 dimensions in this cloud. And so the distance from the Earth to the sun is 1 astronomical unit. That's the definition. So a few hundred times that is still, sort of the scale of, all of the things that orbit the sun and the material that the solar system collapse out of. So again, this is like, really fantastic resolution compared to the scales of the interstellar medium we're talking about, where, individual star systems can collapse and form. So thanks.
Thank you. Another question here from Bill Waller. This one is for Jacob and Josh. I think this is about your very aesthetic pictures on your slides. What is the origin of your intro slide showing Cassiopeia and its environs?
So I think the movie that I showed first, or maybe the picture that you had on your intro slide. The context picture.
Oh, yeah. So the original context picture is from Spitzer, which was taken in 2008, right?
2005 to 2008, a sequence, yes.
Right. So there's images there that show both the light echoes at lower resolution, but also the emission from just general thermal dust. And as Jacob showed, you can really see the contrast where the light echoes have lots of detail because they're being sliced through just in the same way that Danya was talking about. They're being sliced through, so you see all this detail, whereas the stuff that's just glowing in an illuminated way, you're seeing this much more sort of blobby structure because you're seeing the full 3D picture all integrated together.
Rick Feinberg again. So this one's for Joel. Given that the ring has been observed so many times in so many different ways, what would it take? What do we still need to, what capability do we need in order to finally confirm the presence of a companion to that central white dwarf? Is it a bigger telescope? Is it a different wavelength? I mean, how are we going to ever figure that out for sure?
I wish I had a magic wand, Rick, to give you the answer to that question. It's what planetary nebula astronomers tear our hair out about. These stars are extremely luminous. It's very hard to find a faint main sequence or perhaps post-main sequence like white dwarf companion in their general vicinity. In the specific case of the Ring Nebula, well, I suppose if you really did deep near to mid-infrared spectroscopy on that central star, you might be able to find a little bit of infrared excess infrared radiation that would be indicative of a cool companion. That's one way to do it. And other than that, if you have a great idea, please let me know.
Hi, Christine Pilliam from STSCI. A question for Joel. If I recall correctly, there was a 3D model of the Ring Nebula put out based on Hubble data about a decade ago. How does your work compare to what they found?
That's a great question too. So yes, there was a very nice piece of work. It was actually done primarily on the basis of optical spectroscopy, long slit optical spectroscopy by Charles Odell and collaborators. And they published a series of papers. The first one was in 2007 that really dealt with the structure of the Ring Nebula. And I can barely see over here. So our reconstruction, which is actually based on higher velocity resolution than was available in that optical spectroscopy, is confirming much of what the Odell model, it's actually, yeah, what I would call a model that Odell and collaborators put together. However, we're looking at the molecular gas, and we are seeing the velocity clumps that weren't seen in those data. So I think we're able to both complement and extend those results, and that we're also seeing this triaxial ellipsoid that they saw, but we're seeing this additional double polar structure that wasn't clear in those data. These holes that are really clear in the CO that you couldn't quite make out in the optical data because it didn't quite have the spectral resolution that we've got. So it's enhancing those results and it's supporting those results. And if I could ramble on for just another second, the inclination of this object, if you go and look at the literature, has ranged from, we are looking at it exactly pole on to we're looking at it 30 degrees from pole on. And so I think we've now nailed that down. There's no way that we're seeing any structures that are as large as 30 degrees away from pole on in our data. We see no evidence of that whatsoever. The thing is really almost, we're looking right down the barrel of it, which is really quite surprising to me. We're just lucky.
Any other questions in the room or online? If not, You're helping us end exactly on time despite our technical difficulties. So thank you for that. Let's have another round of applause for all of our presenters. Thank you so much to all of you. Thank you to your PIOs for helping to prepare releases and prepare for the presentations. And thank you to all of you in the audience for being here. Our next press conference will be tomorrow morning at 10:15 a.m. And that's going to be a special session commemorating the 100-year anniversary since Hubble discovered the universe beyond our galaxy. So we'll be looking at what we are now discovering beyond our galaxy. Hope to